Well, I have done some work behind the scenes, and the last picture you saw was the little finished gear installed on the gear train, happily spinning away. That will be reserved for a little later on when we do make our spiral or thread-like hob. That is one whose threads are situated or organized in a spiral form, and that needs to be preliminarily cut with a thread cutting operation. That's pretty advanced, and we'll leave that till the second half of this tape. First, we're going to make a simple hob, then one that is not spiral, but instead has rows of cutting teeth set parallel to each other at a distance of 100 thousandths, which will be our the pitch for our 10 thread per inch thread that we want to cut. Not thread, but we want to be able to create gears that have the teeth of them set at 100 thousandths of an inch apart. In other words, having a 10 pitch to them. Now basically what I did was use a piece of rod. This is carbon steel or drill rod, and it's the water hardening variety. This means that when you heat it to a bright red hot condition, you quench it in a bucket of cold water in order to harden the cutter, and that will be shown later on when we have finished not only cutting the grooves but also milling the longitudinal flutes, which will then create the teeth. And you'll see all of that on the mill being cut, and I'll show you how to set that up. But at this point, I want to show you how I set the lathe up in order to cut these little grooves with the 40-degree cutter using the indicator. Well, you should be able to clearly see the tip of the cutter, and this cutter was ground to as close to a 40-degree included angle as I could possibly get it to. I used a little gauge for it. And now what I will do is bring it forward toward the portion. This portion that I machined here will contain the so-called cutting teeth, and that's what we're going to make those parallel grooves. Now what I am doing now is I am bringing the side of the cutter to this edge of the shoulder that I created, and that was machined against the side of that cutter, so that has a 20-degree angle. Now I will back it up at that point, and now I'm going to set my indicator to read 0 against the carriage. We're going to push the indicator all the way in and adjust the needle until it reads 0, which it does there, as you can see. Now with the carriage set at 0 and the cutter set at the end of the shoulder, I'm going to advance 100 thousandths of an inch toward the left or toward the headstock. Now that adjustment we just made looked just like this. We went one full revolution and then brought everything back to 0. If you go beyond that, just back it up and get it as close to 0 as possible. The indicator compensates for any backlash, by the way. Right there. Now the next thing we do is bring the cutter forward until it just kisses the work. And that is happening almost. You just keep turning. There we go. That is now taking off a couple of molecules off that surface, as you see right there. And we back it up, and now the next thing we have to do is set our dials to 0. Now here you see the cross-light dial set at 0, as is the compound dial. So this is our perfect starting position. Now we can continue. Using the dials, we're going to plunge into the workpiece to the correct depth for a 10 pitch 40-degree groove. Now, as always, anytime we're cutting steel, and specifically in this case tool steel, we want to make sure that we have a goodly amount of cutting oil on the surface. And now we will begin to plunge our cutter steadily into the cut. Watching our dial until we reach a depth. In this case, I have determined that the correct depth should be 70 thousandths or thereabouts. Adding a little oil as we cut does not hurt. In fact, it's quite beneficial. We have gone 40 thousandths now. The cut is getting pretty heavy, so we'll add a little more oil. Now we've gone 50 thousandths. $55. $60 thousandths. And we'll go ahead and check how well the cut is going. Let me go ahead and brush off some of that swarf. Now the theory here is that if the cutter is correctly ground and the depth of cut is correct according to the spacing, then the top of the tooth or the groove created should equal the width of the tip of the cutter. Now there's no way I can measure that, but you can visually look at it and determine whether the top, the flat face of the groove is wider or narrower than the flat face of the groove of the female groove you're creating. So everything at this point looks nice. Let's go ahead and continue deepening the cut. We have reached 60. And 65. Now we will retract the cutter so that it clears the work. Remove the swarf. And now we will advance the workpiece over, or should I say the carriage, 100 thousandths, and repeat the same operation. This will be carried all the way across that shoulder until all of the grooves have been created. Now when we make the spiral hub, the spacing will be regulated by the carriage advance, which will be automatic according to our gear train, which is set to take a 10 TPI advance. So we will not have to measure using the indicator. But this method will enable anyone that has even a lathe that does not afford the capability of cutting threads. It will enable you to be able to create a hub that will allow you to make a very nice spur gear. Okay, I had a little bit of a catch there. I was feeding a little bit too aggressively. As I was there. This is pretty tough material. Okay. As we near that full depth of field, we always encounter a little bit of chatter. I'll go back in there and clean it back up again slowly. I'm going to slow the lathe down to minimum speed and take that last cleanup cut. Okay. So as you can see, this is just a repetitive type process in which we just continue cutting the grooves across the work until we have as many grooves as will fit in this particular length of shoulder. Now, theoretically, we only need 5 of these grooves, as the center groove will be cutting the main tooth on the center of the axis of the dividing head, and the upper and lower, this will be placed vertically, by the way, on the mill. The upper and lower or adjacent grooves, top, to the top of it and bottom of it, will be not only cutting but modifying the shape of the tooth that's also adjacent, above and below the tooth we just got done cutting with the central set of teeth, and so on down the line. So you really need one in the center, 2 flanking ones, and then another set of flanking set of cutters, and that will automatically produce the involute curve, even though at this point these are just straight grooves. It's rather ingenious and amazing how this works out, and you'll really enjoy this when you see it actually working. And as you can see, the grooves now have been successfully cut, and I'm going to end up with an even number of ultimate cutting teeth once we mill the flutes, but I will also have that centrally located row of teeth that we are after. Yeah, we definitely need to have that, as it makes the whole process work out to the utmost accuracy that way. Now, as with most things, there's always our little secrets that one picks up, and one of these is that the sharp edges of these 40-degree, now basically just blanks, need to be rounded over a little bit, and for that I use just a simple triangular file, and I just take a single pass in between each one of those. Now that will be cutting the bottom of the tooth on a gear, and the bottom of the tooth does not come out flat. In fact, it should be slightly rounded. So with a slightly rounded upper surface of what will be the teeth, we will get that sought after roundness to the bottom of the gear tooth. That is required so that the meshing between two gears is very smooth, and as one tooth enters the space created by two gear teeth and also exits it, it will be done so in a very smooth manner without any binding at all. Now you don't want to make this completely round. We're just basically taking the edge off. I may look like I'm taking a lot of material off, but I'm just barely removing a little bit of dust off of these edges. Okay, and that's about it. At this point, we're going to transfer this over to the mill and proceed with the cutting of the flutes. I also have to cut a little flat, which will be done by a milling operation, which will locate itself here somewhere. And basically that's so that it can be fitted into the arbor, and the set screw can bear against that little flat, and that way it will lock the cutter in position or securely to the arbor. Okay, now that I finished milling the grooves, I have moved the whole assembly over to the dividing head, which is still attached to the milling table, and I am going to mill a flat so that I can use my set screw on the arbor against that hob, and then that combination will be installed on the dividing head. Right now I got it still attached to the 4-jaw chuck, and then we will begin to cut the flutes. So let's go ahead and make a pass against that surface, and I've already taken a couple of smaller passes. We'll take one last pass just so you see the mill operating in a cutting function rather than gear cutting. This is the type of cut a mill normally makes. And normally this sort of thing would be actually clamped onto a vise, which is a lot more sturdy and secure than the situation we have here, where I have a chuck screwed onto the spindle of the dividing head. I have the work clamped pretty far out, as you can see, and I'm attempting to take a milling cut across it, and that's not the most sturdy of situations. Okay, so that's a pretty nice little flat. Now I'm going to transfer this unit to the arbor and then install it to the dividing head. Okay, at this time I just want to show you what this unit looks like at this point. There's the flat, and now we'll slip it into the arbor. It's a nice, snug, but very true fit. And now we'll tighten the set screw against that flat and secure the whole thing against rotation. Now we'll screw it to the spindle of the dividing head and get ready to proceed to cut those little flutes. Now there are a number of ways we can cut these flutes, and they can be nothing fancy. They can just be grooves, so that we can then grind the teeth back and put some relief on them so that only the points of these teeth actually touch the work. And we can either use a very small end mill, one smaller than this, maybe 1/8 of an inch in diameter, or we can use a slitting blade and take cuts across the teeth, slightly offset to create a slightly angled cutting edges. I'm going to choose to use the little slitting blade. This is a 1/16 of an inch wide, or 62 thousandths slitting blade, and we'll go ahead and install it onto the milling arbor, and then I'll go through the alignment procedures that are required to be able to cut these types of flutes. It's actually quite simple and produces quite accurate and workable type flutes that will allow the teeth to actually cut properly. If you look at a saw blade, you can get an idea of what I am referring to. In fact, this very little saw is a good example of that. Okay, as you can see, I have brought the blade down so that its bottom edge is running along the center line of this workpiece, and basically that's all the offset we need. In other words, if I had put the blade so that the center line of the blade was lined up with the center line of the work, there would not be any offset of the teeth, and that would not work. Okay, let's go ahead and set up to make our first cut. And what I will be doing is I'm going to index this workpiece and create, say, about 8 flutes, 8 or 10 flutes. I haven't decided yet how many. We'll see what the spacing needs to be. It may end up being an odd number of flutes, but the idea being that you should have more than 2 sets of teeth cutting into the gear blank. So that's why I want to have enough of these flutes so that at any time this is rotating past the workpiece, in other words, the ultimate job of this hob, of course, is to create a gear. So for instance, if, depending how thick the gear blank is, if I was to, say for instance, try to cut a very fat gear such as this one, I wouldn't have to worry, as this gear would ensure, this hob would ensure that at least 2 of its sets of teeth, in other words 2 flutes, would be engaged in the work at one time. If only one of them is engaged in the work, that creates some problems, especially with the spiral type hobs. It's not so much of a problem with this type of hob, but it will be a problem with the other types. So let's go ahead and begin to cut our little flutes. Now I want to tell you that the depth of cut for the flute is not nearly as important as the depth of cut of the actual grooves is. In other words, we just want to create a deep enough flute so that it is at least as deep, or if not a little bit deeper than the depth of the grooves. And if you recall, that was 65 thousandths. Now the way we will measure that, very simple, is to bring the X axis toward the blade, and then while rotating the cutter we will advance on the Y-axis until we just begin to kiss those edges. Once that's accomplished, we will zero our dial, just as we did when we were milling the gear teeth on that 25 tooth gear. Here we go, we're kissing the little grooves. So now we'll zero the dial and remove the workpiece away from the cutter and zero the dial. We'll just move it over until the number 0 is in place. There's the number 0. The screw is hiding it, but nevertheless is set at the starting position. And now we will feed the work toward the little cutter about 10 thousandths for our first pass. Okay, before we begin cutting the flutes, we have to do one last little calculation. Now I have decided to put 10 flutes on my cutter, so I have to figure out what number of turns I must turn my 60-to-1 dividing head worm shaft or dial in order to get 10 divisions. Now, our ratio being 60, I divide by the number of flutes or the number of divisions that I need, and that gives me the number of turns, which is in whole numbers, which is nice, of 6 turns per division. So let's go ahead and begin. And here we go. Now I'm going to keep a close eye so that I don't cut into my arbor. It's kind of a close call. Right there, I am at the middle of my last cut. So now I just bring it back and proceed to advance 6 turns. Now of course I had my dial set at 0 before I began. So now it's a simple matter of advancing the number of turns that my little calculator told me. That's 3, 4, 5, and 6. And now we can begin to do the second pass. Now we advance 6 more turns. 3, 4, 5, and 6. And make that pass. Now it's quite apparent that I could have used, say, a 16th inch diameter end mill. They do exist, even that small, and you can see the little grooves beginning to emerge, but I think a slitting blade does a cleaner job and leaves less of a burr between each one of those grooves. It may seem rather tedious to produce this cutter, but believe me, in the end, your labor will pay for itself in a tool that will enable you to cut as many number of teeth in a gear as a full set of 8 cutters, which will run you about $200 plus. When I reach a point where I am almost cutting below the depth of the grooves, I will start adding a little bit of cutting oil to the whole setup. Okay, I have finished milling the 10 flutes, and now I'm beginning to cut the relief angle on top of each row of teeth. And basically I'm doing that with the milling head as I did before, except I'm cutting each of the flutes at an angle of about maybe 10 degrees. Once I finish with the milling operations, I will go ahead and heat treat it. I will heat this to a cherry red, then quench it in water, and then I will sharpen it with a hone. And then the cutter will be ready to be put to use. And as you can easily see, doing it this way, you can do the whole row of teeth in one pass. Of course, I'm indexing 6 turns at a time, as I did during the cutting of the flutes. And I'll finish the whole process by taking one final pass, just taking a skim cut of maybe no more than a thou. Okay, and here you see the finished cutter. It really grabs against my skin very nicely in the correct direction and slips on the opposite direction, as you can see. So the relief angle is perfect. Okay, let's go ahead and heat treat this little tool, and then we'll be ready to test it. I'm going to start heating the business end of this cutter until I get it cherry red. Hopefully I'll be able to do it with this propane torch. That will definitely take a while. It's getting there though. When you quench the tool, you make sure you agitate it quite a bit, as to that way you're able to cool it down as evenly as possible. And now this tool should be glass hard. The next step would be to polish it and to bring it to a light straw color. as you temper it. Although I really like the very dark oxidized color that you get when you heat treat something. That's kind of hard to see. Well, admittedly, that's not as pretty as it looked when it was nice and shiny, but believe me, this cutter is very, very hard right now.